So this video is going to go through and look at the applications of intra and intermolecular forces. So it is making the assumption that you already have some kind of basic concepts and ideas of what intra and intermolecular forces are, which is addressed in an earlier video linked there, which I don't think you can click on. But you can find it in that YouTube channel, and that would be the name of the video. If you are already in Mike's class, which should make sense to you if you were in Mike's class, then you would have seen the above video already in a play pause it before watching this. Okay, so real quickly, our types of forces. Our forces are intermolecular attractions, inter meaning between molecules. So inter, between molecules. And this is different from our intramolecular attractions because intra means within molecules. So intra is within a molecule. One of the initial assumptions that we're going to make when we're talking about inter and intra is that if we looked at, say, a compound, let's call it water, the intramolecular attractions would be shown with these solid lines, okay, connecting the individual atoms. So the intra end up being bonds. The inter end up being kind of implied. An inter kind of requires another molecule to be drawn in. Okay, so if I were to draw in that second molecule, the intermolecular force would be the attraction between one molecule and the other. That is now an intermolecular attraction. Sometimes, okay, not always, shown as that kind of dashed or a dotted line connection between those. What we're trying to do is differentiate that from the intra being bonds. The intermolecular attractions are very often assumed that there are other molecules. So there's not an easy way for me to ghost without just straight up erasing. So I could draw out the water molecule and say, what kind of intermolecular force would water exert in its environment? In that case, what I'm asking you to do is to draw in a second molecule at least to establish what that intermolecular attraction is. So intermolecular is always between at least two different compounds or different molecules. That second molecule isn't always drawn, and in fact is rarely drawn, particularly in Chem 130. Okay, so with that intro, we could now look at our intermolecular attractions. There are three. We have your ionic or electrostatic, and as we talked about before, electrostatic is really just a way to differentiate it from the ionic bond, but it's effectively the same thing. The dipole-dipole intermolecular force, and the London dispersion, van der Waals, or I'm going to go ahead and add some extra terms on here. You can see induced dipole. This one's really irritating to write out, which is one of the reasons why I don't write it out. Induced dipole force. Probably the most accurate of the names. It's also the most tedious to go through and write out. Okay, but that name could also get used. You could even see it abbreviated as just an induced dipole force. So with that, we need to be able to identify each of these forces. So what I would recommend you do is pause the video and try and come up with a definition for each of these three things. If you've already got notes from the past video, don't look at those notes. What you want to try and do is pull back as much information as you can about these three types of intermolecular forces. So I'm going to again request pause, tap space, click the screen, and we're back. When we're coming back and looking at this, our ionic or electrostatic forces are ultimately going to come from ionic bonds. So what does that mean for me? Well, that means that when I look at an individual structure or formula, I need to be able to identify what kind of bond is connecting those. If I can identify that bond as ionic, then I know the interaction or the intermolecular force that this molecule will exert out on another molecule will be an ionic interaction. Okay, and so that's what we're trying to go through and do. Okay, for those of you paying attention, what we just did was defined an ionic force as an ionic bond. That's not a useful definition. I can't apply that. So how do I know I have an ionic bond? Well, I would know I have an ionic bond because I have a metal and a nonmetal. And when we look at sodium and chlorine, sodium's a metal, chlorine's a nonmetal. I now have an ionic bond. So that would allow me to tip off that I'm looking at ionic intermolecular forces. The next one down on the list is the dipole-dipole force. The dipole-dipole force comes from a compound that has a polar covalent bond. Okay? That would mean we have partial charges, and we have that is probably an unfortunate way of showing this. The Greek letter chi, capital Chi, is electronegativity. So we're looking for a large difference in electronegativity. So if I looked to identify a polar covalent bond, carbon to oxygen, okay, how do I know that's polar covalent? Well, that becomes a very challenging question. Okay, so we're defining that we have a dipole-dipole force with a polar covalent bond that doesn't help us out. The other thing we could look to would be the difference in electronegativities. But I'm going to bet none of you have memorized the electronegativities of carbon and oxygen, so we don't know the exact value of that. But hopefully what we can recall is that oxygen is the second most, meaning it is going to generate or pull those electrons towards it, which means the oxygen starts to become negative. Not formally negative, so I can't write it as just a negative sign. This is where I would introduce what is known as the delta notation. I'm using a lowercase delta to represent a forming charge, okay, or a partial charge. Well, if the oxygen's becoming partially negative, the carbon would be partially positive. In all of that, to be able to come to that analysis, I had to know something about those electronegativities. This is why when we talked about electronegativity way back when, we said it was an incredibly important concept that you need to be able to know. Okay? Which is then going to get us to kind of the next point. How can we trigger? What can we look for on this? And the definition right now that I'm going to tell you as your kind of rule of thumb is that it's everything else. Well, what the hell does everything else mean? Right now, it doesn't mean anything until we know what all of our other systems are. So we'll come back to that definition of everything else here in a second. The London dispersion or van der Waals forces, how do we know we have those? Well, those come from non-polar covalent bonds. I tend to abbreviate and just say covalent or polar covalent. So I'm differentiating between those two by adding the word polar. I don't have to add the word non-polar because now it's becoming redundant. This is a difference in electronegativity that is about 0. Okay, so what would our rule of thumb be for that one? Well, the first one's pretty straightforward. If it's 0, it's the same type of element to the same type of element. That would mean we have a non-polar covalent bond. If we have that non-polar covalent bond, that then means we have a London dispersion force when we look at how that molecule interacts with its environment. Okay, you'll note that it says approximately 0. It's not exactly 0. And that's because what we found through experiment is that there was another bond class, the carbon to hydrogen bond, that showed up so frequently in our molecules and compounds, but its chemistry was that of a London dispersion, or it acted very much like a London dispersion interaction, which meant that we had to kind of broaden the definition for nonpolar covalent to include the carbon to hydrogen. Now that we've got our 3 categories kind of defined out, we can double back to our everything else category. That everything else bond is really saying, look if it's a metal and a nonmetal. Really, all you have to do is look to see if it's a metal. Okay, if it's a metal, it's ionic. Is it the same to same? Then it would be nonpolar covalent. Is it carbon to hydrogen? Well, then it's nonpolar covalent. Everything else now comes in as the last stage. So you're really checking 1, 2, 3 things. If those 3 things aren't satisfied, then we're falling in the everything else category, and that by definition would then make it polar covalent and a dipole-dipole force. Is it perfect? No. Is it going to work? Yes. Okay, and so there will be some cases where that doesn't line up perfectly, but it works out pretty damn nicely. Okay. For those of you then being like, well, I thought there was another force. Okay, isn't there another one? Yes, there is. We also get hydrogen bonding. The reason why I pull hydrogen bonding out is that hydrogen bonding isn't really a new force. Hydrogen bonding is a dipole-dipole force. It's just a special case of the dipole-dipole force. Okay, why is it so special? Okay, well, so first off, because we know it's coming from a polar covalent bond, because it's a dipole-dipole, that rule comes into play. The big thing that differentiates hydrogen bonding from dipole-dipole is this and, okay, which is why it's bolded. We're looking at hydrogen bonded to fluorine, oxygen, or nitrogen. Conveniently, fluorine is the most electronegative, oxygen is the second most, nitrogen is the third most electronegative element. Which means when we're looking at hydrogen bonded to any one of those three elements, we are looking at a difference in electronegativity that is massive. It is so massive that it starts to equate to an ionic bond. Because it's starting to mimic that, and that now becomes a force that is somewhere in between the ionic and the dipole-dipole force, which is why hydrogen bonding gets pulled out as a separate thing. It also gets pulled out as a separate thing because of its importance. Hydrogen bonding is very commonly found in the world around us because it is found in water. Water is our classic hydrogen bonding solvent, and water makes up 70% of everything that we really experience. Okay? Because of that, hydrogen bonding got its own kind of moniker through this system. So how do we know we have hydrogen bonding? Okay, well, it's going to copy the rules of our dipole-dipole. It's going to be an everything else type situation. And more particularly, you will also have to see hydrogen actually bonded to fluorine, oxygen, or nitrogen. One big thing to note here is that if we're identifying that connection, that is a bond. That is a bond that is not hydrogen bonding. Okay? The term hydrogen bonding is a horrible moniker because it is not an actual bond. It's an intermolecular force. Okay, why do we call it bonding? Because it was so strong that people that initially discovered and addressed it started labeling the interaction incorrectly. And what they started labeling as the interaction was that bond connecting really hydrogen and fluorine. Okay, so they viewed all of the interactions and weren't able to differentiate between an actual intramolecular bond and an intermolecular force. Hence, we get the confusing moniker for it. It's a big issue. People have talked about it right and left, trying to change the name. The best that I can come up with right now is putting the bonding in quotes. More than likely, it's not going to change because there's now too many people using the term hydrogen bonding, and it's going to be too hard to re-educate the entire scientific community to change that name appropriately. Okay, so hydrogen bonding is not a bond, it is a force. Okay, which then gets us to the next big thing that we could go through. Well, almost next. Yeah, we'll do this. What we want to be able to do is have a rule of thumb. Okay, that rule of thumb is what's showing up in that red box. Okay, these are our thumb rules, if you will. Those thumb rules allow us to be able to look at a compound and be able to swiftly kind of classify the type of interaction that would be coming from it. That type of interaction, as we'll see here, becomes very important because we can use that to predict certain features. Okay, that prediction scale is the next kind of step that goes into this. We would also have to layer in the level of strength. The ionic interaction is a strong interaction. The London dispersion interaction is a weak interaction. And as was presented in the other video that you should have seen already, the London dispersion was such a weak interaction, we said it didn't exist. Okay. Then someone had to come along and be like, well, actually, it is important. We do have to address it. And that's what's happening. Okay. So when we're looking at this scale, we're going from the weak interaction all the way up to our strong interactions. Okay. As far as our intermolecular forces go. Okay. The thing that might you might start to notice is that an ionic bond generates an ionic force. A dipole-dipole bond, a polar covalent bond generates a dipole-dipole force. And a non-polar covalent bond generates a London dispersion force. So you'll probably start to see these kind of connections between them. I saw those connections as well and turned it into this kind of color wheel that's trying to represent the interplay between these. One of the things that is missing is that up at the top here, what we should be seeing is this color wheel stretching all the way from black over here to black over here, red through the middle. Okay, and what's happening is that we arbitrarily, as scientists, went through and cut a line through the middle of this and said that these were bonds, that says bonds, and that these were forces. Really, all that's happening is we have some level of attraction. Where we've decided that threshold is happened to fall right through the middle of our ionic interactions. This is why ionic bonds and ionic forces are very easy to confuse, because they're dividing. They're on the dividing line between those two categories of bonds and forces. So what I've effectively done is then kind of bent that down so that we can then see that interaction around it. Okay, so if we're going to add some extra information on these arrows, so this one around here is going to run all the way around, increasing strength of interaction. A non-polar covalent bond is incredibly strong. Okay, and we'll address some issues here on why that tends to be confusing for people. The non-polar covalent bond is the strongest interaction in this kind of argument. The London dispersion is the weakest interaction. Okay. When we look at the other arrow on the other side, we're saying increasing polarity, and that one's a bit misleading. That one should really run through the middle of this. Oh, that is one of the most god-awful looking arrows ever. Through the middle of this is our polarity arrow. Okay. The polarity arrow only goes up to ionic. Ionic is the most polar. Everything else is less polar. So that the arrows are a bit misleading on this. Okay? But what we're trying to do is show those connections. So that if I have, say, a black non-polar covalent bond, that's going to result in a black London dispersion force. So a very weak intermolecular force. And therein lies the issue with our non-polar covalent bonds. People go through and assume bonds are what are dictating all of our physical properties. And that is just not true. The physical properties are dictated by the forces. So that if I have a non-polar covalent bond, that is such a strong bond that that molecule doesn't want to interact with any other molecules. So we get a very weak force connecting those molecules to each other, which means when I go through to, say, boil it, I don't have to add a lot of energy in, and I phase transition very quickly. Okay? So what people are confusing is that difference between bonds and forces. They are both attractions between each other, but the strength of those attractions are vastly different, and they are interconnected. As we go through and make that intermolecular attraction weaker, say going up to or intramolecular attraction weaker, when we move up to a polar covalent bond, well, now that polar covalent bond isn't as strong within, so what does it need to do? It has to look outside to find something to stabilize it. So it's now going to generate a stronger intermolecular force to help neutralize those charges. Okay? So you could look at it as the non-polar covalent is so strong as a human being that they don't need others to succeed. A polar covalent bond would be someone that may be decently strong but needs some help. Okay? The ionic bond now needs lots of external help to help them succeed. Okay? And so when we're looking at classes and interactions and everything else in our world, that's a lot of what we see in our external environments. Okay? Is how those physical properties manifest. Okay, so those are all the kind of properties that manifest out of this. If we were going to really call attention to the ones that become important for Chem 130, the phase transitions matter. We're looking primarily at melting points and at boiling points. Okay, melting point being solid to liquid, and boiling points being the liquid to gas. Okay, how do we make those transitions? Okay, the other one that's going to show up potentially for Chem 130 would be our vapor pressure. Okay, this goes back to our gas chapter, and it's the amount of gas that is naturally flowing to, the amount of liquid that naturally flows to becoming a gas. Okay, so there's nothing holding the individual molecules together as the liquid, meaning they have weaker forces. If you have a weaker force, your vapor pressure is going to be much higher because there's nothing holding it as a liquid. So it's going to transition to that gas phase more quickly and easily. Okay, viscosity is flow patterns, surface tensions, and then solubilities are going to be the big one. So we're looking at phase transitions, vapor pressure, solubility, and that's about it. Your textbook will address some of those other ones. They're all tied back to this concept of how those individual molecules interact with each other. If you have to propagate through more, or matriculate maybe is a better word, through more chemistry, organic chemistry is largely based on reactivity, and it all comes back to a hard application of these bonds and forces. So if you can pick up some of that kind of understanding of our bonds and forces, organic chemistry is really kind of simple. You're just trying to neutralize and minimize some of these interactions as your chemistry goes. Okay? And I'm sure lots of people can disagree with me. That's fine. So, melting points and boiling points. So, if I remember correctly, the video ended on this slide, but it didn't provide any answers. The difficulties on this is the most difficult one. I don't know why I decided to do the most difficult one at the top, and then the least difficult is down below. I'll do a full walkthrough on the least difficult and leave you to go through and consider what's going on with the kind of intermediate difficulty ones. And then the most difficult I'll also do a full walkthrough on. Okay, so let's go through and address how we could look at 4. How do we decide which one has the higher melting point? Okay, so if we're looking at higher melting points, what are we concerned about? Well, we're talking about how we transition from a solid, yes, to a liquid. Well, what prevents that transition? The prevention of that is your intermolecular force, or your IMF. If I have a higher melting point, I have to put more energy in to break that force, which means higher means stronger intermolecular force. So when I'm going through to predict which one has the higher melting point, what I'm trying to do is identify the intermolecular force that is highest in strength. So we have ionic, hydrogen bonding, dipole-dipole, and London dispersion forcing. Okay? But remember, we don't see those inherently. What we would have to be able to do is to interpret them from the bonds shown in our individual structures down below. So if we go through and evaluate, we would have to be able to convert our ionic into a bond type. That would be ionic. Our hydrogen bonding was polar covalent. Our dipole-dipole was polar covalent. And our London dispersion was non-polar covalent. This is why we started with that slide of trying to come up with all of those comparisons so that we could evaluate these things. So, next phase is how do we go through and interpret some of that? You are responsible for being able to take this formula and turn it into a Lewis structure. Okay? And we talked about this when we talked about Lewis structure. The basic patterns on the connectivity on how we align these things. Our formula is written in a way to help guide us to that Lewis structure. The same deal applies for the other one, and we should be able to jump to that. Do we need the Lewis structure? Well, we'll talk about that in a second. Okay, so let's go through and look at all of the bonds present in our purple structure. Okay, all of these blue bonds that I'm showing have an interesting characteristic. They are all carbon to carbon or carbon to hydrogen bonds, which means those blue bonds are all nonpolar covalent. If they are nonpolar covalent, they lead to London dispersion forces, which are weak, which would mean a low melting point. Okay, so that's not what we're looking for. As we continue through to look at our molecule, we may note that we have the oxygen bond in there as well. Those orange bonds, carbon to oxygen and oxygen to hydrogen, those are dipole-dipole bonds. The polar covalent bonds. The polar covalent bond leads to a dipole-dipole force. If I have a dipole-dipole force, I should now consider, do I have hydrogen bonding? And sure enough, I do have a hydrogen connected out there, so I do have hydrogen bonding as well in this molecule. So if I look at all of the forces, I have London dispersion, dipole-dipole, and hydrogen bonding. When looking at melting points, officially it's the strength of all of the forces, okay, which will become relevant when we look at one. But at a first approximation, we can just go through and evaluate based off of the strongest force. So which one of these is the strongest force? Well, hydrogen bonding. When I went through and did that analysis, I did it based off of the structure drawing. Did we have to go to the structure? Could we have done it from the formula? Okay, well, let's look at the formula. What is bonded to that carbon, most likely? Well, there's a hydrogen right next to it. Yep, which means that's probably a nonpolar covalent bond, which then means London dispersion forces. Okay, if we go through and continue, we might see, and then this is where it's going to become a little bit tricky. We have this oxygen, and then we have a red hydrogen, and I'm going to call it a purple hydrogen. The red hydrogen is the only one connected to the oxygen. Okay, that generates a polar covalent bond, which is now a dipole-dipole, which could lead to hydrogen bonding because we have the hydrogen bonded to oxygen. Okay, the purple hydrogen is officially bonded to, as we see up here, the carbons. Okay, not to the oxygen. So it's not generating a hydrogen bonding force. Okay, that will become relevant when you go through and look at, I believe, actually 2 and 3 both have a system where there are some hydrogens next to oxygen that aren't bonded to oxygen. Looking at the structure helps you see that. Looking at the formula becomes a bit dodgy to evaluate, so make sure you at least understand the notational differences here. We should then go through and do the same argument with our other compound, compound B. When we go through and look at compound B, we're going to end up with our London dispersion forces again. One of the things that's nice is we could immediately ignore those because they were the same in both compounds. As we continue across, we do still have a polar covalent bond in orange, which would be a dipole-dipole force. We don't have hydrogen bonding, so maybe A is going to be the stronger one. What do we have, though? That purple bond is a metal, and a non-metal, we have an ionic bond, which leads to an ionic or electrostatic force. The ionic electrostatic force is the strongest force on my list. Based off of the rules that I just went through and elucidated out here, I want the strongest force for my compound to have the highest melting point, which means my answer is 4B. Okay? All of that was kind of thought process on going through and doing this. And you may think that, God, that's a lot of work. Most of that work can be internalized if you do practice. If you don't do the practice, then you won't be able to do any of the work, and all you'll be doing is guessing. You're getting a 50-50 odds here. Okay? So please spend the time to do the work, identify the bonds, identify those forces, come up with those ranking systems, and it will help out. Okay? The last one that I said that I would walk through, which I might have to erase some stuff for, unfortunately, because that one's kind of long, would be looking at something like this. Okay? For A. So we're going to erase everything else off of this, or most of it off, and try and evaluate this. Okay? In our simple fashion, what we could go through and do is just look at our formulas, That's what I said we could go through and do. We don't have to look at the full-on structures. Okay, if we look at 1A, we have carbon to hydrogen, carbon to hydrogen, carbon to hydrogen. All the atoms in that structure are carbon to hydrogen, which then means we're looking at nonpolar covalent bonds. Nonpolar covalent bonds lead to London dispersion forces. That's the only force that I see possible for this compound, which would suggest that it's not our answer. Okay? When we go through and look at B, we see a similar issue though. All of those are carbons to hydrogens. So it's still a nonpolar covalent structure, which still means London dispersion forces. Okay? So is this then a trick question? Which one has the higher melting point? They have the same melting point? No. Okay? And the reason being is that if you were to say, I don't know, this is my version of a little baby. So there's a little baby crawling on the ground. Looks like a dog. Oh, well. Okay. So there's our little baby versus, let's pretend this looks like the Hulk. Okay. And you had to go through and then fight this one of these two people. There you go. 6-pack, big legs. Okay. And we were going to go through and look at a fight. Well, you would probably say you would rather fight the baby because you could beat the baby, but you aren't going to beat the Hulk. Okay. But what happens if we now change this argument? Instead of now fighting baby versus the Hulk, let's see, can I pull this off? Copy. You're fighting one baby, or you are fighting... Oh, wow. That copy did not work the way I wanted it to. Or you are now fighting still babies, but now instead of just one of them, you have to fight 1,000 of them. Okay? Are you still going to choose how is that going to change things? Okay? And let's ignore the fact that you have to deal with the burden of having dealt with this many babies, however way you want to look at it. Okay? Just battle to death, that's just the way it works. You're probably going to favor one over the two. So the number of intermolecular forces contributing also changes your melting point. When we look at that larger molecule, okay, what happens? Yes, at each individual point of interaction, we generate a London dispersion force. Okay, and that individual London dispersion force is the same strength. But when we look at A, we'll get, say, 4 interactions. When we look at B, we're going to get a whole lot more interactions, which means the sum total of those forces are going to contribute to our melting point, and B ends up being the higher melting point because there's more of those weaker forces present. Okay? So when we're thinking about melting and boiling point, realize that at a first approximation, it's just the raw strength of the intermolecular force that dictates. After that, there are other considerations that need to come in. The size of the molecule, how big it is, how small it is, how folded up the molecule is versus how stretched out it is. There's lots of other things that contribute to melting point and boiling point. The simplest attempt with melting point and boiling point is the strength of the intermolecular force, which means when you now go through and answer 2 and 3, you should be selecting the molecule in each of those pairs that has the strongest intermolecular forces. I'm just going to say you're going to have to ask me what the answer is for those in our conversations through WebEx or in class if this is a much later semester. Okay. Continuing on, phase transitions. I do just want you to be aware of this. Okay, so here's a diagram to kind of represent this pictorially. We want to get an idea of our heat versus our temperature. So I'm going to take a block of ice at a very cold temperature. Okay, so that block of ice I'm going to say is negative 100 degrees Celsius. Okay, and now what I'm going to start to do is add heat to it. Okay, when I add heat to it, what's going to happen to the temperature? Well, the temperature should start to rise. as I add that heat in. Okay. As I continue to heat, though, eventually I'm going to hit the temperature of 0 degrees Celsius. Now what happens when I add heat? What's going to happen to the temperature? Okay. For those people saying, well, it's just going to continue to rise. Okay. Does it, though? Okay. If I take a block of ice and I slowly heat it up to 0 degrees Celsius, and then I continue to add heat, does the ice all of a sudden go up to 5 degrees Celsius? Okay, or slowly go up to 5 degrees Celsius? It's progressing upwards, or does it stay at 0 degrees? Okay, and that becomes kind of a challenging thing to observe on the solid side of it, on our ice side of it, and it'll be a little bit more sense on our gas side. As we add heat, the temperature actually is not going to change. It's going to flatline at 0 degrees Celsius. Okay, but eventually what happens? All of that solid ice becomes a liquid. Okay? Once it transitions to be a liquid, as I continue to add heat, the temperature is going to rise again. Okay? Eventually, again, it's going to hit a spot where it stops rising. Okay? At 100 degrees Celsius, I've now added enough heat that the temperature gets up to 100 degrees Celsius, and again, it flatlines. So this is where I said it makes a little bit more sense. Think about when you boil water. Okay, you boil water, it gets to 100 degrees Celsius. Does that mean all of the water instantly became a gas? No, you're still adding heat and it's still boiling, but the temperature doesn't change. The temperature is only changing when you're just a single phase. So what's happening in each of those kind of flatline areas? Well, those flatline areas are our phase change. It takes energy to change phases, to go from, in the red phase, liquid to gas, and in the blue one, from a solid to a liquid. Okay? As soon as we convert all of the liquid across to a gas, well, then again, our temperature climbs. Okay? So you may have heard references to caution, steam in these lines, caution hot, freak out about it. People are like, well, it's only 100 degrees Celsius. How bad can it be? No, it's not 100 degrees Celsius. If you see a steam line, it's probably not at 100 degrees. It could easily be clearing 200 degrees Celsius. We're looking at a gas that could theoretically be infinitely heated. So it could be infinitely hot. Liquid caps at 100 degrees Celsius. Solid ice caps at 0 degrees Celsius. You can get really, really, really frostbitten, okay, by touching ice that's at the bottom of the Antarctic. Why? Because it's probably a lot colder than 0 degrees Celsius. And so brief contacts with that could result in instant cellular death. The same thing is happening with our gas at the high end. We could go to not infinitely low temperature, we could go to 0 degrees Kelvin, and then we have an infinite max on our heat. Okay, let's ignore the phase change to plasmas. Okay, so what I want you to be aware of is these phase transitions. You are still constantly adding energy in. Where this becomes kind of interesting is, say, if you move into 151 and we want to know how much heat was put in, there's going to be a heat associated with that phase change. There'll be a heat associated with this phase change. There'll be a heat associated with the change in temperature. Okay, so if I want to know the total amounts of heats being transferred, because remember, I can't directly observe heat, I can only measure temperature. If I want to figure out what that heat is, I would have to kind of monitor the temperature and make these kind of correlations back using a diagram like this. Okay, and that's kind of neat. Okay, that's really all I want you to be able to think about and recognize, is that there is heat involved in a phase transition that does not change the temperature. A big new section in 151, for those of you that go there, is a section on thermodynamics, which is all about heat transfers. Okay, and that becomes a big deal. Okay. Vapor pressure, another application of our intermolecular forces. This is kind of a fun question for me personally. I like this. Okay, so let's go through and walk through high vapor pressure. What does it mean to have a high vapor pressure? That means there's lots of gas. Well, if we have lots of gas, and this is lots of gas above a liquid, right? If I have lots of gas above a liquid, what does that mean about the intermolecular force? Well, then that must mean that the intermolecular force is very weak. Okay? Why does it need to be weak? Well, that's why it's transitioning to the gas phase. Okay? It doesn't need a lot of energy, and so it's jumping from the liquid to the gas right away. If I have a weak intermolecular force, that means I would be looking at a strong bond. Okay? Our weak intermolecular force would be, say, London dispersion force. A strong bond would then be a nonpolar covalent bond. Okay? So I have to be able to reason through each of these steps. So now that I have these kind of steps in play, I can now go back and look at my answer choices. If I look at answer choice E, that is all nonpolar covalent. Nonpolar covalent. Whoops, S is now fitting in our everything else category. S to C isn't in one of those places. Since it's not a metal, it's not ionic, and since it's not carbon to hydrogen or same to same, that must mean that that's a polar covalent bond. That polar covalent bond is going to lead to a dipole-dipole force. That dipole-dipole force, if we had our kind of chart memorized on our strength of our interactions, is kind of a middling intermolecular force. Okay, it's definitely not the weakest, okay, but it's still pretty on the low end. So we would continue that analysis through all of these. D, C's, and nonpolar covalent, nonpolar covalent, nonpolar covalent, chlorine. Chlorine's a dodgy one because it looks, depending on who you talk to, like uranium if I wrote it, or it looks like carbon as part of the carbon backbone. Okay, that chlorine is now a carbon to chlorine, which fits in our polar covalent, which means dipole-dipole. This should already set up alarm bells in our head saying both D and E are wrong because they have the same strength force. As we continue through C, nonpolar covalent, nonpolar covalent, nonpolar covalent, that oxygen to C is again going to fit our polar covalent category, which means dipole-dipole. Okay, again, that fits in our category of the others, so all three of those are the same. It's going to be hard to differentiate those. B, nonpolar covalent, nonpolar covalent, nonpolar covalent, nonpolar covalent, nonpolar covalent. These bond in that compound are very strong bonds leading to very weak forces. Nonpolar leading to London dispersion. That London dispersion, being a weak force, satisfies the conditions that we walked through initially. So B is looking like a pretty good answer. Let's take a look at A, nonpolar covalent, polar covalent. Right away I can stop that analysis. This is going to be a dipole-dipole, okay, which means I can get rid of it. And B ends up being my answer now because it has the weakest force. So this relatively quick interpretation of what those statements mean. What do the words on the page mean? Lots of gas above a liquid. Okay? That then means weak intermolecular forces. That then means strong bonds. You now have to be able to look at those answer choices to identify the bond types so that you can identify the force types. And that allows you to make these conclusions about physical properties, which is pretty freaking cool. Okay? Which is now going to transition to our last major category, looking at solubility and miscibility. Solubility is the class of anything dissolving in a liquid. Anything. Miscibility is the ability for a liquid to dissolve in a liquid. So miscibility, if we look at this, is a small category within solubility. Okay, which I think are Venn diagrams. Okay, the big thing that we would use for this is primarily realize that when we're looking at this section, we're talking about nonpolar covalent compounds. The rules for ionic compounds, which is kind of asked later in the slide here, the rules for ionic compounds go back to our solubility rules. So you would need to use your solubility rules, that's referencing our double replacement reactions, okay, to dictate how our ionic compounds dissolve in water. What you're using here are how our non-polar or covalent compounds interact with water. And the rule of thumb that comes out of that is typically the statement of like dissolves like, which I find a horrible statement because it's too vague. Really what we're talking about is like forces dissolve like forces, which means, yet again, you have to be able to look at two things and you have to be able to very quickly evaluate what kind of forces come out of it. Water is a polar covalent compound. That polar covalent compound leads to dipole-dipole forces. Because I have hydrogen bonded to oxygen, nitrogen, or fluorine, I have hydrogen bonding. When I go through and look at the next one, CH3, that is a non-polar covalent bond, which leads to London dispersion forces. Those would be very different than hydrogen bonding. If we look at our curve, hydrogen bonding's up here, London dispersion's down here. There's a large gap between those, which means they shouldn't interact, or they should not mix. They don't have that like dissolves like aspect. As we continue through that compound, we have another CH3, which is going to be another nonpolar covalent, and then we get up to this OH, which is now a polar covalent bond, which leads to a dipole-dipole force. Because we have a hydrogen bonded to oxygen, we now have hydrogen bonding. And sure enough, these forces are similar. Okay? So if you were worried about trying to kill, say, the coronavirus, you might be mixing ethanol, CH3, CH2OH, and maybe a little bit of water, and trying to wash your hands off with that. Remember, the percentage of your alcohol has to be 60% alcohol in that water. Okay? So if you're anything under that, you're probably best suited to just drink it and drown away the sorrows. Okay? Don't do that because you need to be focused and studying chemistry. When we move to the other system, so this first one, these would mix, these would be soluble. Okay? When we move to the next one, we'd go through and do the same analysis. Water we just went through and did got us to hydrogen bonding. If we go through and look at that other compound, nonpolar covalent, London dispersion force. What happens when we look at the next one and the next one? Still nonpolar covalent, London dispersion. London dispersion and hydrogen bonding are different. These would be insoluble. They do not mix. Okay? So all we're really trying to do is to compare the forces between those compounds. If the forces are the same, we call them soluble. If the forces are different, we call them insoluble. These are a prediction based off of some relatively simple observations. And we're picking the strongest force in each of these cases for those individual compounds and how we would evaluate and process them. Okay? It's shown as an actual multiple choice. Apply the like dissolves like rule. Notice again, this is not a question written by me because I would say like forces dissolve like forces. Rule to predict which of the following liquids is miscible with water. So when we go through and look at this, we see miscible, okay, which is really just them trying to confuse you. This is the same thing as soluble. Okay, we're talking about them actually mixing. So this is same forces. Okay, so that's what we need to find. Which answer has the same force? Therein lies a problem. These are same forces between two things. Okay? Our answer choice is very clearly one of those things. What is the other thing? Where's the other structure? This is where we have to read the question carefully. The other structure, they didn't give us as a structure. They wrote it as a name. That would be H2O. H2O is going to give us hydrogen bonding as a force, as we've seen in the other cases. So what we would now go through and do is look at each of these formulas and trying to decide what would be the strongest force. You'll notice in these compounds, they're only giving you formulas, not the full-on structural formula, so the individual connections between it, which is ultimately a way to simplify this. If we only have carbons and hydrogens, by definition, that's going to be nonpolar covalent and London dispersion force. That is not similar to hydrogen bonding, which means probably not A. Look at B, look at E. All three of those have the same kind of parallels, which means they would be very difficult to differentiate from each other, so we should eliminate those from our answer choices. When we go through and look at C and D, C brings in this chlorine, okay? So we're now looking at a connection between carbon and chlorine. That would be a polar covalent bond, which would lead to a dipole-dipole force. No hydrogen bonding, though, because we don't have hydrogen bonded to oxygen, nitrogen, or fluorine. Dipole-dipole isn't super similar to hydrogen bonding, but if I was given the choice between A, B, C, and E, C is the best answer. Okay, does that make sense? So note, we changed the question, the answer choices, A, B, C, and E. Okay, C is the best option to dissolve because it is the closest in intermolecular forces. Okay, but what does D give us? When we go through and look at D, we should hopefully see that we have the CHs, which is going to again be nonpolar covalent, London dispersion forces, but we should also notice that we see this OH floating out there. That OH is going to be polar covalent, which is going to lead us to dipole-dipole. Do we have hydrogen bonded to oxygen? Indeed we do, and we have hydrogen bonding. What force is the most similar to water's hydrogen bonding? Hydrogen bonding or dipole-dipole? Well, hydrogen bonding, glycerin is the best of these choices to be miscible with water. And what we've done is evaluate solubility based off of those intermolecular forces. And with that, we've actually finished our intermolecular force lecture. So thanks for listening, and sorry it was so long.